Okay, I started recording. Whenever you're ready to go for it.
Okay, great. Let me put here in chat the link to the GitHub repo, and please clone or download this repo if you haven't already. This will be a courseware they're going to work through today. And the cool part about this is if you run out of time today, or if you're not able to finish a particular section, you can definitely come back and continue on, which is really cool. Kubernetes hands-on workshop. You can get to this by going to robrich.org and click on presentations. And here's Kubernetes hands-on workshop right here at the top. So Kubernetes hands-on workshop. The first step is for us to install. Well, hopefully our internet will come back on and we'll be able to do some interesting things on camera. In the meantime, though, yeah, let's dig in. So Kubernetes hands-on workshop. Our goal today is we're going to get Kubernetes installed in your environment so that you can start to play and continue to learn in your space. Next up, we're going to get you familiar with Kubernetes and help you get some of that skill, some of that muscle memory, some of that experience. So intentionally, I'll invite you to install Docker on your own machine. The first step here, and hopefully you've done this already, is installing Docker Desktop. Docker Desktop is a great Kubernetes runtime environment, but the only one. So if you have trouble with Docker Desktop, down here at the bottom are some instructions on installing minikube. And you could choose minikube, or you could choose micro K8s, and each of those as well. So in Desktop on Linux, it's a little bit involved because you don't have that same virtualization piece, but on Mac, it's actually super simple. It's amazing how simple it is. You just
Rob,
grab Docker and you add.
Sorry to cut you in, but it looks like it's breaking.
That's it. It's breaking.
Yeah, I can.
Let me try something. Turning the camera back on again.
Yeah, now it's much better.
Sure.
Very nice. Then it sounds like it was indeed that. It was the echo in the room. Interesting. I'm kind of but yeah. Okay, installing Docker. Ideally, you've done this already. If you haven't, then now's probably a great time to start installing Docker. If you're on Linux, then, just did that again. Zoom, hide. Okay, if you're on Linux, the install instructions for Linux are kind of involved because we don't have the same level of virtualization. But if we're on Mac, it's super easy. Drag the Docker app to applications. If you're on Windows, it's a bit more involved. You have to turn on virtualization in your BIOS. It may already be on, but if not, I don't know the password to your BIOS either. So slam your F keys as you boot and see if that pops up a menu like this. You'll find something that talks about virtualization technology, and you need to turn that on. Once you've got that on, then it's a lot simpler. You can just go straight to Docker Desktop for Windows and install it, and it'll start to do some of this install as well. But just in case, installing the Microsoft Windows Subsystem for Linux, or WSL, the virtual machine platform, the WSL update, setting the version to version 2, and that will get you to the point where now Docker Desktop will install just fine, which is pretty sweet. So once you've got Docker installed, then let's verify that it works. Type docker space -- version, and then docker run hello world, and you should get something like this. So CLS docker -- version. Now we're not super worried about what the version is. Ideally, you're on 1903, but if you're not, then as long as you're on 18 or so or better, then you're probably okay. But if you're on 1 point something, then it's time to update. Then docker run hello world. Now in this case, it couldn't find the image locally, so it pulled it. That's great. And then it just ran this and it showed that it worked. Cool. So if you can get to this point, then you've got Docker installed and we're ready to begin, which is really, really cool. Next up, enable Kubernetes mode. Right here, we'll right click and we'll say settings. If you're on a Mac, then you'll grab the whale up in your top toolbar and go to settings. Here inside settings, go to Kubernetes and turn on Kubernetes mode. The first time you turn on Kubernetes mode, it will take a good while to get Kubernetes containers downloaded and started. So it's not stuck, it's just, yeah, this takes a long time. And thus, hopefully you've already done all of this part so that we can dive straight in. The next thing for validating Kubernetes, we'll run Kubernetes or kubectl version. So we'll say kubectl version. And now we get the version. Now, if you're on 1.16 or 1.18, you're probably okay. We're less concerned about the version number and more concerned about kubectl version replying correctly. Once we've got that, we can take a look at kubeconfig get context. And if you had get contexts, if you had Kubernetes on your corporate laptop and you had it hooked to your corporate Kubernetes instance, then you just want to make sure that the star is right here next to Docker desktop. If it's not, you can say kubectl config use context Docker desktop. But for most of us who just installed Docker desktop, then it's definitely going to be it'll be on Docker desktop already. And you probably won't have other instances. You'll just have the Docker desktop. Perfect. So we've got Kubernetes installed. Now we want to start downloading some images. This will also take some time. Docker pull node:\alpine, Docker pull this .NET Core SDK and .NET Core ASP.NET. We'll use each of these 3 images throughout this course. So fire it up and start to get those images installed. And let me know in chat if you're having issues, and we'll definitely dive in. Meanwhile, let's dig into what is Docker. Well, why are we going to start with Docker? This is a Kubernetes class. Well, Kubernetes begins with, so I have a Docker container. And because it starts with, so I have a Docker container, then we do need to ensure that we get a Docker container to begin with. So let's take a look at what is Docker. And we'll see how Docker then ties straight into Kubernetes. Cool. So we did that hello Docker. If we do Docker run hello Docker, or Docker run hello world, it'll do a whole lot more than is obvious here, which is really, really cool. But what we got here was this really elegant startup experience. So when we look at Docker, we're like, well, isn't this just VM++? Isn't this just, the next level of virtual machines? Well, it is, but it isn't. Because with Docker, we're not virtualizing the hardware, we're virtualizing the operating system, the kernel. Docker is ephemeral, isomorphic, and deterministic. What I mean by that is they're short-lived, they're unchanging, and they're the same every time. We have this configuration as code metaphor in Docker that allows us to build things exactly the same every time. So, well, I have Terraform or Ansible or Puppet or Chef for that. Well, yeah, but Docker is ever so much more than that. Because it's this ephemeral, isomorphic, deterministic mechanism, it's an ideal platform for dev and ops to share so they can clearly delineate the duties. Developers can build the containers, the images, and operations can host those containers running inside of a Docker hypervisor. So like any good story, we just started in the middle. Let's start at the beginning. Docker. Docker is an ecosystem around container virtualization. What do we mean by container virtualization? Well, it's lightweight kernel virtualization. We're virtualizing the operating system. And that's really what makes containers so much different, is that we're not virtualizing the hardware, we're virtualizing the operating system, which means we don't need to boot another copy of Windows. We just need to launch the process inside Windows, or Linux in this case. So what is Docker? It's the suite of command line tools for creating, running, and managing these containers. The analogy I like here is, what's the difference between XML HTTP request and AJAX? Well, XML HTTP request and AJAX are technically the same thing. AJAX is the way is what we call it, but we use XML HTTP request or fetch to be able to get that content. So similarly, Docker didn't invent virtualization. C groups and namespaces and jails existed long before Docker came, but Docker made it really easy to use these pieces. And so by extension, it made it really effective for us mortals to create these. And that's really cool. XML HTTP request was really hard to use. AJAX is pretty smooth. C groups and namespaces are hard to use, but Docker containers are pretty nice. So I think as an industry, we're almost past this slide, but let's zoom in just a little bit and take a look. In a traditional virtualization experience, I have this hypervisor, maybe this is Zen or VMware, and then I have various VMs on top of that. Now, here's my VM. I installed Ubuntu, I installed some dependencies, and I installed my application. I wanted another copy of this application, so I cloned this virtual machine. Now I have a second copy of Ubuntu, a second copy of my dependencies, and a second copy of my app. I installed a third one. Maybe this is Red Hat or something else. And you can see that we've got a lot of duplication here. We have this big operating system piece. By comparison, in Docker, we have the Docker hypervisor. Now, like Zen and VMware, the Docker hypervisor creates that sandbox around each of the containers running in it. So I can't just reach out into another one's process space. I have to communicate over a network. But unlike the other hypervisors, I'm only virtualizing the operating system. I'm not virtualizing the hardware. So we only need our dependencies and our application. So you can see that I was able to spin up a whole lot more containers than I was to spin up virtual machines in this experience. Now, this is definitely not to scale, but you can see that straight away, we have a whole lot lighter weight mechanism for running our applications. When we're running in containers, we don't need another copy of the operating system. We only need the difference between this host kernel and what we need to run our application. So containers. Containers need to virtualize and share the host kernel. So containers must run on the kernel for which they're built. Linux containers run on a Linux host, and Windows containers run on a Windows server host. What's missing? Well, what about Red Hat and Ubuntu? What about GNOME and KDE? Can I run GNOME kernels or GNOME containers on a KDE host? Or can I run Ubuntu kernels on a Red Hat host? What we're virtualizing is the kernel. And the kernel underneath Ubuntu and underneath Red Hat is the same kernel. The kernel underneath KDE and GNOME is the same kernel. We don't need to craft a new kernel to be able to get at that content. Now, if we're running a Windows container, we can't run that on an Ubuntu host. We need to run that on a Windows server host. But if we have a Linux container of any kind, we can run it on a Linux host of any kind. That's really cool. What else is missing here? Well, you and I are on laptops or desktops. We're not on a Windows server. Maybe we're on a Mac. So, well, how will we do Windows desktop and how will we do Mac? I already downloaded that Docker for Windows or Docker for Mac and it installed just fine. Are you telling me that that's not a thing? Well, it is and it isn't. Here in development, we'll probably do something like this. In production, we definitely want to run this way. We want to run as densely as we can to get maximum value of our hardware. But in development, we'll probably do something like this. So I have my Windows laptop, I have Windows, I have a Hyper-V hypervisor, and inside Hyper-V, I have this guest OS, this Docker desktop virtual machine. And inside that guest OS, I installed Docker hypervisor, and then I can run my Linux containers. Now, the Linux containers are sharing this Linux operating system, which is on this hypervisor on my Windows operating system. Or maybe the Docker hypervisor is on the Linux operating system on my Mac laptop. That's perfect. Because I have Hyper-V or I have HyperKit, I can also install other virtual machines on that and do just fine. This, as we installed Docker Desktop, it created this virtual machine for us, and it created this Docker hypervisor. If we're running inside of WSL2, then it actually did some WSL2 magic. So for example, WSL list-v, here is my regular WSL instance, and here's my Docker desktop content. And so because my Docker desktop is running inside WSL2, I have that Linux environment where I can do the really cool things around running Linux containers on Linux on top of Windows or on top of Mac. That's really cool. Any questions so far on Docker and virtualization?
Yes. Hi. Yeah, I put this in the chat, but nobody's answering it. I have to go. And is this going to be recorded? And how would I access it later?
That's a good question. Mrinmoy, can you tell us about the recording and how we'll access it later?
Yeah, it is already recorded. And at point of time, you can have where you are clicking for the live stream, the same place you can have the recording.
Yeah, so just we'll post a recording later today or in a few days. We just have to copy it to YouTube and then we'll link it over here.
Thank you.
Will
Thank
I
you
find
very
that
much.
link in Whova?
Yeah, you just have to click the link in Whova, it'll show up. But it'll be a few days.
That makes sense.
Okay. Thank you very much. I appreciate it.
Yep.
Welcome.
Thanks for joining us as long as you could, Les. Good books. Good question. What books do we have in this space? Docker and especially Kubernetes is moving fast enough that by the time we get the Dead Tree edition, I don't know, we may not be up to speed. So I don't have any good recommendations for Docker books. That is a great question, though. Thanks for the question, John. Okay, let's dig in. So the Docker ecosystem, here's where the magic really starts to light up. And this is so cool. We have a Docker file. And this Docker file gets built into an image. This image gets hosted as a container on a Docker hypervisor. The Docker file is that configuration as code. It's the instructions that tell us how to build up an image. Now, thus far, I've been using image and container as synonyms. I'm going to stop doing that. Image is this binary blob that is that we build from that configuration as code piece. So we'll take our Docker file and we'll explain all of the details of how to build up this image, and we will build that image. As we launch the image, we launch it as a container inside the Docker hypervisor. Now, the cool thing is we can also share images with Docker Hub or pull images from Docker Hub. As you started pulling the Node and Nginx images, or actually just the Node image, then you pulled it from Docker Hub. Now, we didn't need to recompile it once we got it down. We're actually sharing the binary blob. That's really cool. We'll get a chance in this workshop to actually share an image with Docker Hub, and that will be really fun. So I have a Docker file that I build into an image. I may choose to pull an image from Docker Hub as well, and I can run that image here on the Docker hypervisor. I can also create a Docker Compose file that will start up or build many images and run many containers in something like Docker Swarm. That's really cool. The Docker Compose file then specifies all of the details for either the Docker files or the images on our Docker registry to be able to build or spin up, build or pull all those images and spin them up together, linking those microservices together. A Docker file, that configuration as code, gets built into an image. The image gets started in a Docker hypervisor. And this is that workflow that makes this process just really smooth. Okay, installing Docker. We saw the instructions there. And so if you're viewing this presentation from elsewhere, then these might get you through it. I love this because on Linux or Mac or Windows, the install is pretty smooth, but let me just show you because it's entertaining. Oops. The other, reopen. The install instructions for Docker on Windows Server. It's kind of involved. So yeah, that's kind of funny. Okay, Docker desktop. It automatically spins up that VM. It connects the Docker command line to the VM, and it proxies localhost traffic to the containers, which is really cool. Here's an example of a configuration as code Docker file. So we'll say from node. How did I know what node was? I went here to Docker Hub. Let's go hub.docker.com. And I want to start a node app. So I'll say node, and I'll search for node-like containers. Here's one. Oh, hey, this one was created by the nodejs.org. So now I've got this official image, and it'll tell me the different things that I need to do. Now, there are various tags, and in this case, I'm not using any tag. So I just say from node. Cool. Now I pull that image from Docker Hub, and that will give me a good starting point. I'll say workdir is /app. That's my base directory. It will create that directory if it doesn't exist. I'll copy my package.json into that current directory here specified by workdir. And then I'll run npm install to get all my dependencies. I'll copy everything else. I'll set some environment variables. I'll expose port 3000 so that others know how to connect to this container. And then as the container starts up, it will run cmd npm start. So this is that configuration as code. This is that piece that allows us to get to how we start up this image, or how we start up this container, how we build the image and start up the container. All of the commands besides cmd get run at Docker build time. So at the point where we get to the image, the cmd command gets run as we start the container. So all of these will run at build time. This one is the one that runs at runtime, that Docker file. Each one of these lines will create a new layer in the Docker image. And the cool part is that each layer is ephemeral. It doesn't change. So once you have that layer on disk, you have that layer. And if I build a new image that has different layers, like maybe I change my source code, then you'll download those new layers, but these original layers you'll keep with the ones that you've already downloaded previously. So there's kind of those 4 words in a Docker file: from, run, copy, and CMD. There are definitely others, and we saw some others as we looked at it. But if you know these 4 words, you can probably read almost every Docker file, which is really cool. From, what image do we start from? Run is run some shell command. Copy is copy something from the host machine into your container. And then CMD is the thing that you want to start up as you start the container on a Docker hypervisor. Cool. So we talked about the layered file system a little bit. Let's dig in a little bit more. The layered file system, each command in the Docker file will create a layer. So I like this graphic of how to kind of look through it. Let's say this is our base layer. And on the base layer, we're going to add file 3 and file 4. Then in the next line of our Docker file, we're going to add file 2. In the next line of our Docker file, we'll add file 1, we will delete file 3, and we will add file 4. Or actually, we'll modify file 4 in this case. Okay, so now our image has these 3 layers. That's cool. As we start our container, it's just kind of like looking over the top of this, and it sees file 1, file 2, there is no file 3, and there is a file 4, the modified one here from this image. So as we build up each step in our Docker image, we'll get this layered file system. And this layer then can modify files underneath, but the files underneath are still there. File 3 is still here in this base layer. I just don't see it as I start up my container. I love this. So the layered file systems, once I have that layer on disk, I don't need to re-download it. So if I create this image, and then later I create this image, you don't need to re-download this layer. You already have it on disk. That's really cool. So with that node, we have that node server layer. Then we say expose 3000. Then we say server.js, the workdir app. Each of those are layers in our image, and they start from this node image. Here's this node image. And if we come to latest, we can take a look at the Docker file that they used to build their image. Okay, so we're going to set the node version. We're going to install some things, some GPG keys. We're going to go grab some the tar.xz, and we're going to untar it. We'll install yarn. Here's some more copying to copy this Docker entry point into place, which is pretty sweet. And it says from build pack deps stretch. Okay, so build pack deps. Let's come back to Docker Hub, and we'll search for build pack deps. Here's that build pack deps image. And if we look at stretch, where is stretch? There's stretch. We can take a look at the Docker file that built this one. So that one does these commands. It installs gcc, ImageMagick, a couple of other things, bzip2, and it's based in build pack deps stretch scm. Okay, so back here, build pack deps stretch scm. Here's the Docker file for that one, and it will do some more content, and it starts from stretch curl. So we can come back here, stretch curl. It does this thing. And so we can see that each one is standing on the shoulders of giants. This one starts with Debian stretch. And so eventually we'll get down to from scratch. And from scratch is really interesting. That's the base of the tree. But we can think of it, turtles all the way down. Here's the images. Here's the layers for my image. Here's the layers that I'm built on top of. Here's the layers that it's built on top of. Turtles all the way down. What's cool is once I have this layer on my drive, I don't need to do anything weird. I already have this layer. So no matter how big this image is, I grab it exactly one time. Problem solved.
Yep. Rob, one question in the chat window.
Yes. We create the Docker file and run it to initiate the image, correct? Yes. We use the Docker file to, let me go back to this graphic. We use the Docker file to build the image, and then we will run the image as a container. Great question. So the Docker file then is indeed that root of the tree. And with that Docker file, we can get back to everything else. That was a great question. Very insightful. Thank you. What other questions do we have right here?
No more question, Rob, as of now.
Very nice. Okay, so we have layers, we have turtles all the way down, and this is all of the things to build my image. As I start up my image as a container, I'm going to get this new read-write layer. This new read-write layer sits on top of all of the other pieces, and that's the thing that is different for each container. If I spin up 2 copies of this image, I will get 2 different copies of this read-write layer. So if I go change any of these files, those changes will end up in this read-write layer, but they won't alter any of the images layers underneath. Once I stop that container, then I only have the image, and so that read-write layer goes away. Ephemeral hardware. I spin up a new one, I kill it off. That read-write layer is that magic piece that allows me to edit the files on disk. Well, kind of, tell the container I'm editing the files, but it doesn't actually change any of the underlying pieces. So if you pop my container and hack it up and do all the things and then go delete the stuff, well, all the stuff is still there. I'm just going to kill off that container, spin up a new one, and I've just defeated your hack attempt. That's pretty cool. When we run a Docker process from an image in detached mode, how can we interact with the container from the shell once it's running? Great question. When we get to Docker run, let's do exactly that. We're going to look briefly at volumes, and then let's look at Docker run. Volumes. So a volume is like a symlink. I want part of this container to be a little bit more durable than just having it disappear. So I'm going to have this puzzle piece, but I'm going to store this puzzle piece on some external drive. As I start up the container, I will map that puzzle piece into place so that the container just believes that it's part of the file system, but now I can store those files in a much more durable place. So to pull that off, in my Docker file, I'll specify a volume. And here's that Docker run command where I say -v. I'm going to map my current directory into that container as that volume. So in a similar way, where we can say Docker run hello world, we can also say Docker run, and I would like you to map the C users Rob desktop into /data. And I will tell it it is a volume. Now, in this case, hello world doesn't know anything about /data. So of course, this will map the volume and the container won't care. But that's how we'll spin up a container with a volume. And that's how we got to see the Docker run command. That's really cool. A Docker file gets built into an image gets run as a container. So if I have the Docker file, I can build the image. If I have the image, I can run the container. But I don't necessarily need the Docker file to be able to run the container. I only need that image. That's cool. Some cool reference pieces: Docker build, Docker image list, Docker image RM, and we'll get to play with this quite a bit. So I'll cruise through these quickly. But if you want to come reference these in the slides, then you definitely can. Cool. Craft a Docker file, build an image, run a container. We had this Where did it go? Apologies, I'm making you dizzy. Right there. Here's this Docker file. Let's go build that. So I'm going to, here in this demo folder, I'm going to spin up a web server. So let's create a hello world.js, new file, server.js. And I will go grab this detail from node.js.org. I'm going to come here to about. I'm going to grab this content right here, and I'm going to paste it into place. I am going to remove the host name because otherwise it will only bind to localhost. I don't want it to bind to localhost. I want it to bind to everything. And now let's go build that Docker file. New file, Docker file. Now it's important as we build this Docker file, it is named Docker file, not dockerfile.txt. From node, we got that from Docker Hub, workdir/src, copy in all the things. We'll copy it from our root directory on our machine to the directory that we specified in the image. Here's that image, the /src directory. Then I don't need to npm install because I don't have any dependencies here, but we could run npm install if we wanted to. I'm going to expose port 80. No, let's expose port 3000, and we will set node port to 3000. That tells both node that it's already hard coded to 3000. Perfect. So we'll just expose port 3000, and cmd will be the command that we run, node server.js. Cool, our very first Docker file. Docker build -t hello node dot. And that dot is what directory will run the build command from. Oh, apparently I need to, let me actually do this a little bit later. I'm going to use the Alpine variant of node that will be a lot smaller. Docker build -t hello node. And now I won't need to pull that image. Cool. Ooh, there's no package JSON. You're right. Let's comment out that npm install. Docker build -t hello node dot. Docker run hello node. Okay, so now I've got that container running and it's listening on port 3000, but I haven't really told it how to connect to port 3000. So if I go here and say, go browse to it, then of course, it's gonna go exactly nowhere. But my container is running, which is really cool. Docker container list. I see that container and it's running. Let's stop and remove this container. Docker container stop, that one. Docker container rm, that one. And now we've got that container removed. Well, once my shell catches up. Yes, good question, Anthony. That's why we don't necessarily need the Docker file to run the image, because when we said Docker run hello world, it pulled that image from Docker Hub rather than building it from a Docker file. Exactly. Docker run, I'm going to give it a port, and I'm going to say, I'd like you to map 3000 outside my, actually, I'm going to say, I want you to map 4000 outside across the Docker switch to 3000 in the container. And I would like you to start this hello node. Cool. Now if I come to, now it says it's running on port 3000. It is, but I've mapped port 4000 outside my container. So let's go to localhost 4000 and we'll see this web server. There we go. Hello world. Perfect. Control C, Docker container list, and I can see this container right there. Now I could say Docker container stop and give it some of this container ID, or I could use this image name. But I can also do the stop and RM at the same time. So I'm going to say RM-F 8153. And I only need to give it enough characters to make that unique. Problem solved. So Rishav asks, how do we interact with it? Docker run. We did this -p 4000 to 3000. Hello, node. But now let's run it in detached mode or daemon mode, -d. Okay, now we've got that container started and it kicked off that entire ID. So let's say Docker exec -it for interactive terminal. That's how I remember it. I'm not sure exactly what it means. That, and then what do I want to run? Well, I want to run a shell. Okay, now I'm inside that container and I can look around. So cat server.js, I bet cat is installed. There we go. So there's the source code that built it. Now I could definitely go change this container. I could go modify things. That's not what we want to do. We want this to be ephemeral isomorphic hardware. We want it to be unchanging and short-lived. So even if I did say, I don't know, move server.js to foo.js, that's not a good idea. Let's not configure our containers that way. Let's configure them instead in this Docker file. If we want this to be foo.js, let's name it foo.js. We want these containers to be isomorphic, ephemeral, isomorphic, and deterministic. Cool. So we got our first container running. That was cool. Now, what did it do? It downloaded the node image if it needed to. It started a process. It assigned that a virtual IP, and it natted traffic into the container, which is really cool. Let's see. Do we have the? Oh, yep. And so that NAT is particularly cool. If we want to run another container, we just Docker run it again. That's really cool. A good rule of thumb, and we'll hit this a bunch of times today, we have one container for one process. So how do I run two different things in one container? Well, I don't. I run them in two different containers, one for each process. Docker will start to monitor that process and get a feel for how that works. And it'll kill off that, if that process becomes inconsistent or unresponsive, it'll kill off that container and start up a new one, which is perfect. If we have two processes running in that container, we don't have that same level of understanding and expertise there. Okay, so I talked about how it natted across the Docker hypervisor. We can think of the Docker hypervisor here as like a router. Now, the router in my home, I have the WAN side for the public, and I have the LAN side for all my devices on my network. Now, if I want somebody to come into my network, I may have them come in on a particular IP address. Maybe this is example.com. And then I may choose to port forward things onto the LAN side to a particular container. So in this case, Docker will, the WAN side is localhost. It's not quite localhost, but it proxies it to make it feel that way. And the LAN side is 172.17.0.1. So when I say localhost 4000, it goes, okay, let me route that off to this container. Perfect. If I map a second container, maybe I'm going to say this one is 4001, it will go to this container. And all of that magic is here inside the Docker hypervisor's router. it does that NAT into its own network. So we spun up a virtual network. That's really, really cool. Here's that map. So maybe localhost 80 goes to this container, and localhost 81 goes to this other container, and localhost 82 goes to this other container. And now I have 3 instances of these running, all hosted on port 80 inside this virtual network, and I can access them from different ports outside the network. When someone wants to share a Dockerized project with someone else, should one move the project onto Docker Hub or push it on Git provider like GitHub or Bitbucket? I would say do both. Share your Docker file on GitHub and push the image onto Docker Hub so that people don't need to recompile it to use it. Great question. So we talked about customizing running ports. That's how we do it, which is really cool. Here's customizing volumes and the start command, some other Docker logs. This is really fun to get at the console logs associated with container. But I think I've been talking long enough. Let's dig in. This is really fun. If you haven't already, please download or clone or fork this repo. If you want to, you can just download the zip and unzip it. And our first task is Welcome to Docker is the presentation we just saw. Here's a link to those slides if you want to go view them again. And our next step is to build an image. Now in this folder, I have 2 folders, the done folder where I've solved this problem and the start folder where I have instructions for you to solve it. So yeah, you could definitely look at the done folder and copy them into place, but I would invite you instead to follow these instructions and build your first container. Any questions before we begin? Awesome. Let's spend a dozen minutes building our first container. Fire into step 2.
Hey Rob, should we pause recording for?
Sure. Or we can edit this in Camtasia after the fact. Which would you prefer?
Anything's fine.
Okay.
I could just pause it now and then play it back.
Yeah, sounds great. Saying remove the hostname parameter, do you also want to remove the console log statement? It's less important to remove the console log, but if you'd like to, you most definitely can. Were you able to get Docker started and spin up that container? It's still building, but I think so. Very nice. So who was able to get Node running? And by comparison, who has Node installed on their machine? That's part of the magic of Docker, is exactly that. We were able to run software without installing it. And the moment that we're done is the moment that we can stop and remove that, and there is no registry creep, there is no stuff stuck in our user local bin folder. We're able to install and use software really fast without any mess. We ran Node without installing Node. That's cool. Next up, we're going to look at a multi-stage build. Now, in the in Node, we don't actually compile it. We just kind of deploy our source code. In .NET, we actually will compile our source code and run it. So let's do a quick demo. Are we unpaused?
Yes, Rob. Yeah.
Perfect. So I'm going to say .NET new MVC -- name site. And this will build a site folder. And let's go build a Docker file for this process. Now, if you're unfamiliar with .NET Core, that's totally fine. Let's walk through some of the processes that we need to get this Docker file built. We're going to create a new file. That's our Docker file. And we're going to create another new file. We'll call this Docker ignore. Now, a Docker ignore file is not that unlike a git ignore file. In fact, the Docker ignore file has exactly the same syntax as a git ignore. So we'll ignore bin obj. We'll ignore, those are our built assets. We'll ignore temporary files, star.user, star.suo. There might be a .vs folder if we're inside Visual Studio. And so all of these pieces we don't want to end up in our Docker file. Perfect. Now our Docker file let's head back over to Docker Hub and we'll take a look at the content that we have in Docker Hub, hub.docker.com, and we will search for .NET Core. And we get to this repository. Now here they talk about the various repositories that they have in .NET Core, and we want the build tools. We want to be able to build inside the container. So let's go grab this Docker build, and we want this one from there. Now let's go look through the tags because we kind of skimmed over tags previously. Here are the, we are here. Tags. Here we go. Here are the tags that are available on AMD 64 Linux. We have the latest, which is the default, which we'll use. Now, that doesn't necessarily mean it was the last one published. It's like main or like trunk. It's just a naming convention. And so if you don't specify the version, you will use latest. And that's built on top of Debian. Now, that's interesting, but Alpine Linux is so much smaller. So we have this tag 3.1-Alpine, and that will make our builds so much smaller. Perfect. So instead of 3.1, we will use 3.1-Alpine. Let's copy in all of our content from the directory on our host to the directory in our image. And what directory is that? Workdir/src. There we go. That's the directory. Now, the commands that we would use to build and publish our site is .NET build -c release. So build in release mode, .NET publish -c release, and we'll give it an out directory of /dist. And before that, we'll need to do .NET restore to restore all our NuGet packages. Restore. Okay. So those are the commands that we would want to run from a PowerShell or from a command prompt. And so to run them as Docker commands here in this build file, we'll just say run. I'll run .NET restore, run .NET build, and run .NET publish. Okay. We need to set some environment variables. Let's go look at those environment variables. Right there. So we'll need to set some environment variables that will tell us to start on localhost 5000 and expose port 5000. And then CMD, we will say .NET site.dll. Well, site.dll actually isn't in the source directory. It's in the dist directory. So now we have our Docker file. Now this Docker file will work just fine. We could choose to publish this, but it has our source code in it. It has the build tools. And so that might be a little bit heavier than what we'd like to deploy. Let's come back in here to Docker Hub, and we can look at some other ones. Oh, here's ASP.NET. That only includes the hosted runtime. Perfect. So now we'll go grab this. And it also happens to have a Alpine tag. That's perfect. And let's say from this. So we have one image here that is our build server, and we have one image here that is our runtime server. Let's make those comments. So production runtime, and this one is build server. That isn't a great analogy, but that works. Now we can move this to, I don't know, let's call it app. And now instead of, now we need to copy the files into place. Let's copy them from the dist folder into our current folder. But the dist folder actually is over here, not on our host machine. Copy by default would copy from our local machine. So we'll say from equals build. Then we'll tag this one as build, so we know what stage that is. So after it finishes building this and gets that dist content, it will then start up on this one. And when it gets here, it will copy this dist folder from this build image into place in this image in the current directory. We have created a multi-stage build. Here's one stage for our build server. Here's one stage for our production runtime. Now, as we Docker build this, we can say Docker build -t hello.net, and then the folder that we're going to build this in. Now that will build both stages together. So here's that first stage, .NET restore, .NET build. Is our build going to run? Let's look for the projects that we need to build. It looks like, yep, that build succeeded. Great. .NET publish, that will publish all the content that we need to be able to host into this dist folder. There's that content, and we successfully built it. Docker image list. Now here in the image list, I now see two things. I see that hello.net that I just built, and I see this none. That none represents the image that the first stage that we didn't care about, the one that we threw away. But it keeps it so that next time we say .NET build, it'll say, hey, nothing's changed. I've cached all the things. I don't need to reinstall those. In our next exercise here in step 3, we're going to build a multi-stage build. Once you get through step 3, we're actually going to, I'll throw you in the deep end, and we will do a bigger site. And this is really cool. Step 3 got us a .NET backend. Step 2 got us a node front end. And so we're going to put those together. Here in a bigger site, we have a back end and a front end that we get to build. I have all the source code for both pieces. So here's that .NET backend, but we're going to build up this Docker file. So I would invite you to fill in all the commands that gets you to build up this multi-stage build. Similar thing on the front end. Here is the Docker file that we'll start with. And I would invite you to convert all of these shell commands into the appropriate Docker commands. So let's dig in and let's spend, maybe 20 minutes or so doing step 3 and step 4. Any questions before we dig in? Awesome. Well, let's spend about 20 minutes building these two. And if you have any questions, set them in chat or feel free to unmute yourself and let's dig straight in. Feel free to pause if you'd like.
Yeah, sure.
Good question. Here, when we had these shell commands, we talked about how we could transform them into Docker build commands, but I suspect that's not what you're asking about. You're asking about this. From a shell, this terminal, we can say Docker run like that. Are those the questions? Is that the shell that you're curious about, Amundi?
Yeah, cool. Rob, Amodini has replied back. Yeah.
Perfect. How could I phrase that better to make it more clear?
So I resumed the recording, Rob.
Okay. We have about 7 minutes left, I guess.
Okay.
How are people doing on this? Are there any questions that you're stuck on? Anything that I can help?
Yeah, please feel free to unmute yourself or type your question in chat.
Yeah, whichever way you feel most comfortable with.
No more questions, looks like. So I am pausing the recording.
Sounds great.
Okay, thank you.
And dig back in. I love this because we now have the two pieces. Oh, sorry. Are we unpaused, Minroy?
Sorry, I was on mute. Sorry. It was my fault. Yeah. It's already unpaused. Yeah.
Perfect.
Yeah. I was talking.
Okay.
On mute. Yeah.
So what I love about this is that we have the two pieces. We get to experience building a container that doesn't require compiling beforehand. So we only have a regular build. We get to experience a container that does need that build. So we get a multi-stage build. And we also got to experience getting to communicate between the two pieces. That's what this multi-stage build was really, really great at, is being able to talk to those two pieces, or with the bigger site, getting to talk to those two pieces. Next up, let's dig into Kubernetes, because Kubernetes is so much fun. And if you want to get caught up in if you weren't able to finish and want to get caught up, that's totally fine. We'll start to leverage these containers that we built in a bigger site in subsequent examples. So we can definitely come back to that. But let's dig into Kubernetes. Any questions on Docker before we spin up Kubernetes? What surprised you about the exercises? What did you find interesting or fun or unusual?
Hi, participants. Please feel free to communicate with Rob. Whatever channel you were comfortable, through chat, or you can unmute yourself.
And I'll continue watching chat. I see that some questions have come in through the Q&A, which I'm still not quite sure how, but that's cool. Oh, what exactly is copy ... doing? How is that referencing more than the current directory? Yes, exactly. It's pulling the current directory from my host machine into the current directory of the image. Exactly that. So here we said, copy all of the files from this directory on my host machine here into the directory on the image here. So that then when I ran .NET Restore and .NET Build, all those files were available. If I didn't have this copy, or if I had commented it out, then I would go to .NET Restore and .NET Build, and it would say, I have no source code. Great question. That was awesome. It also looks like I need to scroll more aggressively. Ooh, the exact error that I got. That's cool. Glad you got to find that one. Kubernetes. So we talked about how Kubernetes begins with, so I have a Docker container. And that's why we focused on building up a Docker container so that we could use that to play with Kubernetes. Now, there are other ways to get containers to run in Kubernetes, but for the most part, Docker is the way to do it. Okay, so what is Kubernetes? Well, it's an industry standard mechanism of orchestrating containers. It was originally built by Google, but it's now owned by the CNCF. I forget what CNCF stands for. CNCF.io, the open source holder of all things container and cloud, which is really cool. It isn't the only orchestrator, though. What is an orchestrator? What is this orchestration engine? Well, given a cluster of machines, then we specify the desired state that we'd like. For example, I would like 3 copies of my website running, or I'd like 2 copies of this container and 4 copies of that container, Or I'd like a copy of this container running on each node in my cluster. Or I'd like 3 instances, and I'd like to make sure they're across availability zones. I can give it that desired state, and the orchestration engine will make the decisions that it needs to see that come to pass. Now, there is desired state configuration in Windows, and this is not that. But rather, I'm handing it a desired state. I'm handing it my desired outcome, and I'm letting the orchestrator choose how to do that. Should I schedule this pod on that machine or on this machine? Those are decisions I don't need to make. The orchestrator is going to make those decisions for me. I just tell it what I want, and it accomplishes that. What's really cool then is if that machine becomes unavailable, I don't need to do anything. I told the orchestrator I want 3 copies of my website running. If one of the machines in my cluster goes down, it will spin up the other copies of my website on a different machine. I may get a text in the morning that says, hey, your site was moved to a new container, a new host, or I may not. I don't need to know. I just said, hey, orchestrator, go figure out all of those details. And it does. It's perfect. So orchestration engines. There's a bunch of orchestration engines: Kubernetes, DCOS or Mesosphere, Docker Swarm, Azure Service Fabric, Amazon Cluster Service. These are all mechanisms for running containers. And ultimately, I don't have an opinion about which one you should choose. There are definitely advantages and disadvantages to each. So I would invite you to go into your IT shop and say Kubernetes and Docker Swarm, and somebody's going to talk to you for an hour about why this one is the correct choice for you. And I agree, that is the correct choice for you. But we're going to choose Kubernetes for this course. So Kubernetes, it hosts containers. It hosts Docker containers, and it also hosts other types of containers. But for the most part, Docker containers are really the only kind of containers. So we'll just say Kubernetes begins with, so you have a Docker container. We talked about Docker, so we'll cruise through this. When I'm pitching this to audiences just as a talk on its own, then we dig a whole lot more into Docker. But I'll stop here because this is particularly cool. We use the same tool between dev and ops to be able to get these containers in place. Inside the container, we can decorate it to be exactly the way we want. We can build up the config file just so. We can arrange the curtains on the window. We can set the papers out on the desk. We can build up all of the files exactly in that right directory where we want them. Then we close the lid on our container, and outside the container, we can think of this less as a snowflake and more as a universal standard box. We plug in Ethernet, we plug in power, and up pops the container, and it just works. So containers as that concept is a really elegant way to be able to communicate between dev and ops. Inside the container, we can think of it as a machine, a sandbox. It has a unique IP and a host name. Outside the container, we can think of it as a process. It spins really quickly. We can constrain its resources, the amount of RAM and CPU that it needs to. And in particular, it just boots really fast. That is cool. So we talked about the Docker ecosystem, where we have a Docker file that builds into an image gets run as a container, and that process is really cool. We just learned a whole bunch of Docker things and Docker Compose things, and it's like, well, how's this gonna change when we get to Kubernetes? Well, like this. Here's all the Docker bits. We're gonna keep the Docker file. We're gonna build a Docker image. We're gonna share those with Docker Hub. But rather than running on Docker machine as our Docker hypervisor, we'll run on Kubernetes. Rather than a Docker Compose file, we'll use Kubernetes YAML files to specify the content that we want to run on our Docker hypervisor. We're using Kubernetes as that orchestrator, that mechanism to be able to wrap all of the pieces in interesting ways to ensure that they're running. If we only need one container, Docker works great. If we need to have lots of containers running in concert, we need them to be able to automatically restart and gracefully upgrade, then that's when we'll pull in Kubernetes. Kubernetes is Docker hosting at scale. Any questions on Kubernetes so far? Okay, Kubernetes. So all of the things that we learned in Docker, Docker build, Docker push, Docker pull, all of those will keep using, but we'll replace Docker Compose and Docker Swarm with Kubernetes versions of these. So it's not like we need to throw away all our Docker knowledge. And if you're coming from Docker Swarm or Mesosphere or some of these other service fabric, then all of your Docker knowledge will translate really, really well. That's why we spent the first little bit of this experience learning about Docker. But now we're going to replace some of them with Kubernetes pieces. Let's kind of dig in and take the cellophane off of Kubernetes. We kind of have three main pieces in this orchestrator, this mechanism of communicating between components. We have kubectl, the CLI, we have master nodes, and we have worker nodes. We could also call this the control plane and worker nodes. Okay, so, well, what are these pieces? When we start up any Kubernetes tutorial or when we're looking at any Kubernetes intro video, they'll probably show you a diagram like this, and they'll say, ta-da, I've explained it. I have no idea what you mean by this. Okay, this is going to be cool. This is probably the first and last time you'll need to know this at this size, but let's take a look. So the developer is using the kubectl command line. They connect to the API server. The API server is running on the control plane, and the API server then will get connected to from various pieces. That API server then is kind of the broker of all the things. We'll have controller managers. The controller managers will pull against that API server to see if you've made new things. So the developer commits a new thing. It lands in etcd. The controller manager notices that thing and tells the scheduler, hey, you need to do something. There's something that they want that isn't there yet. The scheduler will pick one of the nodes in the cluster to run. So here's the other machines in our cluster. And let's say that the scheduler picked this one. It talks to the kubelet, and the kubelet then will spin up a pod that will do the work. A pod will wrap your container. So in addition, we have users that will come in. They'll probably hit a load balancer. They'll come into kubeproxy, and kubeproxy will forward them to the correct pod. We have cAdvisor as well as other components that will monitor the pods and report their health back to the API server that'll get stored in etcd. So the developer, the API server, the controller manager, the scheduler, the etcd, the kubelet, the cAdvisor, the kubeproxy, the load balancer, the pod, all of those pieces are interesting, but this is likely the first and last time you care about it at this scale. The punchline here, though, is that all of these are microservices. Kubernetes gets microservices because Kubernetes is built on microservices. And in particular, each of these things, those microservices, can easily get replaced if you have other pieces that you would like to put in place. So if you don't like how the scheduler works, you can put in your own custom scheduler. Or if you don't like how cAdvisor works, you can put in your own custom monitoring solution. Kubernetes gets microservices because Kubernetes is microservices. As you came in and spun up Docker and you turned on Kubernetes mode, it probably downloaded a lot of things. Docker image list, we can see all of these containers that start with gcr.io, that's all of the pieces of the Kubernetes ecosystem that work in all the things: kube proxy, API server, scheduler, controller manager. Those are all of the pieces of Kubernetes, all of its containers that do stuff. That's really, really cool. But again, we probably don't care about it at that level. We'll just say the control plane does all the things. But before we leave this, any questions here on the different pieces inside Kubernetes? Awesome. So installing Kubernetes. I love this part. I went to a conference where a friend of mine went to a Kubernetes workshop. It was actually a 3-day workshop. The middle of day 2, he's telling me, we've almost got it installed. Now, Kubernetes has gotten a little bit easier to install since then, but here's my rule of thumb. Step 1, don't install Kubernetes. It's hard. So, well, why is that? Well, if you're using a public cloud like Azure Kubernetes Service, Amazon Elastic Kubernetes Service, Google Kubernetes Engine, you have Kubernetes at the push of a button. You can just log in, you can push go, and you can get to the spot where Kubernetes is running in your cloud without having to install anything. If you're on a private cloud like Mesosphere, OpenStack, Cloud Foundry, or lots more, then you have mechanisms built in for spinning up clusters. Kubernetes. Oh, they've changed their site. The list of providers is no longer here. Production environment. Oh, bummer. They had this great page. There we go. Turnkey Cloud Solutions. They had this great page of all of the providers, and it was just a wall of images, wall of logos. Now, we talked about the various orchestrator engines, and we talked about how Kubernetes was one of them. There's also Mesosphere and, wait a minute, Mesosphere. You telling me Mesosphere can launch its competitor? Well, yeah, Kubernetes won. Kubernetes became kind of the dominant mechanism. And so Mesosphere has actually worked to replace their underlying mechanism with a Kubernetes mechanism. That's kind of cool. Okay, so if I'm on a local environment where I don't have a public or a private cloud offering, Docker Desktop, we saw how easy that was to spin up. We could also use minikube or micro K8s. K3s is really interesting in that K3s will run on Linux and just spin up the whole Kubernetes stack really quickly. If you didn't use Docker Desktop, you might use minikube, where you just pass in the driver, and you might say, I want to use minikube on top of VirtualBox, or maybe on Mac, I want to use it on HyperKit, or on Windows, I want to use Hyper-V. And all of these pieces, you can just spin up really quickly to get a local Kubernetes cluster running. So step 1, don't install it. Well, yeah, I don't want to completely dissuade you. If you really want to install Kubernetes, then by all means, it's not as hard as I made it out to be. You want to search for kubeadm, or you can go to the Kubernetes install docs, and you can get Kubernetes set up pretty easily. Installing Kubernetes is quite the journey, and it could be a lot of fun. Okay, Kubernetes elements. So there's various things inside Kubernetes, and there are definitely lots more than we have listed. We have pods that specify wrappers around containers, deployments that will give us scale and automatic restarts. We have services that will do load balancing for inbound traffic, And then we have a bunch more. We have ingress and replica set and stateful set and job and cron job and secret and config map and persistent volume claim and stateful set and daemon set and on and on and on. And there are plugin mechanisms where you can load custom ones too. But let's just focus on pod deployment and service, because those are kind of the root elements that'll get us in place. Let's take a look at a diagram of how this works. So if I wanted to start with these pieces, here's a user that connects to an ingress. An ingress will then connect to a service. A service will load balance across a pod, a group of pods, and a pod is a wrapper around a container. So let's dig into each of those pieces and understand a little bit more about how they work. So an ingress is the thing that will convert a host name into traffic coming into the network. So for example, if I go to example.com and that lands on my ingress, ingress will listen only on port 80 and 443. That's just what they do. And it will then link out to a service port. Okay, so this service port, it was specified that it should connect to this service, and this service port then will listen on port 3000. So the ingress notices that example.com came in and it forwarded off to this service. So the service listening on port 3000 will then load balance across all of the pods. And it will just do a round robin. It actually does sticky sessions, which is really cool. And configured in this service is this target port that tells me what port on the container I should connect to. Okay, so the service connects out on port 3000. The container is listening on port 3000, and that connection is made. User to ingress to service to pod to container. Ingress maps the host name to the service. The service load balances across all the pods, and the pod is this really cool network boundary around a container. Under the hood, the pod is actually running Docker commands to spin up or spin down or monitor that container. The pod is interacting with that container provider. Any questions on the Kubernetes elements before we start spinning up some Kubernetes YAML? Great, let's dig in. Okay, so each element, each YAML file in Kubernetes will have four main properties. We'll have an API version, a kind, a metadata, and a spec. We can think of API version and kind like namespace and class name in source code. Metadata is kind of that meta information around the thing. And then the spec is the actual details of how to build this thing. So in metadata, we'll probably give it a name. We might give it some labels. We could think of these kind of like hardware tags. And then in the spec, we'll say, oh, and by the way, I want you to use this image and bind on this port. All of those details will go in the spec. Now, they can be YAML or JSON. Technically, you could use JSON, but nobody does. All of the samples that I can find are in YAML. And so YAML being a superset of JSON, it's just a different format for JSON. It just has less curly braces. So if you're poking at Kubernetes files, I would invite you to get really comfortable with YAML. But squint hard and you can just think of it as a JSON file. Okay, first stop, let's look at a pod. Now, a pod is that definition of how to host the container. So when we ran Docker run, we said Docker run, and we passed it this image name, and we passed it the ports with the -p. This just specifies all of those run details. We're still doing Docker build to build the image, but once we've got that image, we want to run it as a container. Now here, this actually is a containers array, and we talked about how the rule of thumb is one process for one container. The other rule of thumb is one container per pod. A pod is a unit of scale inside of Kubernetes. And so if you have multiple containers running in the pod, you can't scale them independently. Now, there is a time for having multiple containers in a pod, and when you're familiar with sidecars, then definitely take a look at this. But for now, let's give it that rule, 1 container per pod. So yes, in this array, we'll have exactly 1 element. And then here is that object definition that describes that container. So if we were to do this in YAML, we would do it like this. But if we were to do it in JSON, we would do it like this. Containers. Here's an array. And then we will have 1 object that has a name that is nginx and an image that is nginx 1.19.3 and ports, ports. And that is an array because I have the dots again. And then I will have a single thing in my array that is container port 280. Here it is in YAML. Here it is in JSON. And so we can see why they kind of prefer YAML, because it's a lot denser, a lot tighter, a lot terser. Now we could definitely do either one, but that's why we tend to favor YAML. So actually, while we're here, let's fill out the rest of this and build up the YAML. Here's the YAML. And if we were to do this fully in JSON, we would say API version is v1 and kind is pod and metadata is an object. And inside that, we have name is nginx, and we have labels that is an array. And here inside the array, we have app is nginx. Outside the metadata, outside here, we have the spec that it too is an object. And inside the spec, we have a list of containers. And we've just gone full circle. Cool. So let me do this side by side because that'll be kind of cool. Here is that pod definition as YAML. Here is that pod definition as JSON. And they are exactly identical. But in this case, it was 12 lines and it was really terse to read. We didn't need a whole lot of quotes. Here it is 21 lines. And it's kind of involved. I actually cheated because this actually ought to be its own line. And that makes it even more lines. Now, as we start doing this, we could create a label. Let's say we want to say version is 7. Well, the JSON for how this would turn out is version is 7. But we need this to be a string. And so we could put this in quotes, or we could just make it a string, v7. Now, because it's v, then it will automatically build it as a string. So that's just one of the things to keep in mind when you're doing YAML. One of the questions is like, well, why don't I have another dash here? Well, it's because this is that whole object, and these are all of the pieces in that object. Why do I have to put the v here? Well, because I want it to be a string here. So YAML. YAML is interesting and annoying, but YAML is kind of cool. But it is YAML. So 2 spaces. That's the rule of YAML. You have 2 spaces. Not 4, not 3, not tabs. They are 2 spaces. Thanks, Google. So Yeah. Any questions on YAML? Okay, so we dug into a pod, and let's look at what we built with this pod. We have a name of Nginx, we have labels, and these are like hardware tags, so we could specify as many as we wanted. Spec, we're detailing how to build up this pod. Well, here we have a list of containers. We have one container in that list, and it has an Nginx 1.19.3 image. Perfect. Now, a pod is that unit of scale. So we want one container per pod. We'll list the Docker image and the ports, and that will give us the details that we need to be able to spin up this pod. But probably we're not going to build a pod on its own. Instead, we will build a pod as part of a deployment. A deployment will specify details about how to start and restart and scale pods. In particular, how many instances of a pod, and it will explain the definition of how to build a pod. So in the example, we're definitely going to go build up a pod, but we'll do that so that we can see which properties are pod properties and which properties are deployment properties. So here's a deployment. Now, in the majority of cases, we're going to get in here to this template, and this template looks awful lot like a pod. And in fact, that's exactly what it is. This is a pod definition. Metadata, labels, spec, containers, image, ports. We've got all of the pieces of the pod here in this template. Outside the template, we have a selector that identifies which pods it controls. We have replicas. So in this case, it's going to spin up 3 copies of that, 3 copies of the pod. And we have some other metadata that we've seen. The API version and kind, so the namespace is apps/v1, and the class name is deployment. Perfect. So this deployment then specifies that I want to go build up this container, and I want to do that 3 times. Now, there are some properties in this deployment that we didn't specify because we want those things to get auto-generated. So you notice that we don't have a name property here. If we specified a name, then the deployment would spin up 1 copy of that. Then it would go to spin up a second one, and it would say, hey, wait, I can't create a duplicate pod. I already have one with that name, and the deployment would fail. So by not specifying the name here, we can get it to auto-generate a name. Perfect. The other thing we don't specify in the template is the API version and kind, because of course it's a pod. So we've got a deployment. Next up, let's talk about a service. The service is the load balancer over the top of deployments. So deployments and pods say nothing about how to get traffic into it other than the port that the container is listening. All of that is part of the service. The service will identify the ports that it's listening on and the pods and containers that it will forward traffic to. So here's a service definition. API version and kind. So this is in the namespace v1 in the class name service. It has some metadata like a name. In this case, we called it Nginx service. We could call it Nginx as well because a service is different than a deployment. So we could name them exactly the same. We've got some labels. App is Nginx. And we've got this type of node port. We've also got the ports. So it's going to listen on port 80. And because we didn't specify the container port, or the target port rather, it will forward off to port 80 as well. Now we did specify node port. Let's dig into a little bit of the types of ports. Now this gets a little bit weird, but it's cool. Ultimately, these are load balancing across all of the different pods that match this selector. So let's dig into selectors. Here's selectors, then we'll come back to the service ports. So in my service, I have this selector that says app of Nginx. So it's going to go find all of the pods, whether created by a deployment or not, that have metadata labels app Nginx. Now they may have other metadata labels as well, but they must have these metadata labels. they must have all of them. So if I specify 2 or 3 or 4 labels here, then all the pods must have exactly those labels, and then maybe some more. So in this case, in my service, I said selector is app nginx. So back here in my deployment, here I said labels app nginx, so that I know that this service is the one that's going to proxy into all of these pods. This deployment will spin up 3 of them, and the service will load balance across all of them. Now I do have this match labels here just so that the deployment knows which containers it's managing. But if I were to leave this off, it would do that automatically as well. Any questions on deployments and services so far? Awesome. Well, let's dig in. We talked about type node port, and I glossed over it a little bit because service types get a little weird. The first type of service is a cluster IP. And this cluster IP type is one port for the entire cluster. So at this port, here's port 80. If I connect from any container to my cluster on port 80, I will get forwarded to this service. Now that's cool, but I may end up going across machines in my cluster. So if I have 2 nodes, I would go out from my one node and I would go into the other node, even if I had a copy of this container running on my same node. Okay, both port and target port are required. If we don't specify the target port, it will actually just use the port. But in this case, it's kind of like that router where it takes a request in on port 80 and forwards it off to the target port of port 8000. How do I search a pod from a different cluster according to the metadata tag of the pod or FQDN or IP address? Good question. Let's come back to that when we dig into kubectl, but I love that. That is such a great question. Okay, so cluster IP, it must have a port and a target port, and it'll default the target port to the port. In this case, I'm going to accept connections on port 80 and forward them off to the container on port 8000. Next up, we have a node port, which is a superset of cluster IP. I suspect the majority of the time you'll only use node port and the other types of services will be less relevant, but just in case. So this adds a node port. Now, this says port 80. That's actually a typo. Node ports are between 30,000 and 32,000. And so I'm going to write that down to go fix that. 36. To go fix that typo. Okay, so a node port is the port on that particular node in the cluster. So if I want to communicate without going across machines in the cluster, I can specify the node port. And now I've got one port that all of the things can specify. Now, node port is public across the cluster, but it's also public outside the cluster if we don't have a firewall that blocks ports, node ports coming into our cluster. By default, all of the public clouds don't allow connections to node ports, so we can pretend that they're private ports internal to the cluster. So we still have target port and port. Those are required by cluster IP, and this is a superset, but here we are. And then we have type load balancer. Now, the cool part about load balancer is that not only do we have port, node port, and target port, but we also have load balancer IP. This gives us a truly public thing. The cool part about service type load balancer is that it will spin up a hardware load balancer in the public cloud that you do this on. So if I do this on Amazon, I'll get an Amazon Elastic load balancer. And if I do this on Azure, I'll get an Azure load balancer. And I didn't need to specify anything interesting. I just need to say this type is load balancer. Now, depending on your cloud, if you spin up a second service of type load balancer, it may reuse that load balancer, or it may spin up a second load balancer. So these could get decently expensive because I may spin up one piece of hardware per microservice. So just be careful of that. If you need an easier way to do this is with Ingress, and Ingress doesn't have that same one load balancer per service type of experience. Okay, so we have these three service types. We have, well, if I didn't have a service, then I wouldn't be able to get traffic into the pod. We have cluster IP that is one internal port on the cluster. Node port that is a public port on each worker node, thus, public routable from outside the cluster. And load balancer that spins up the cloud's native load balancer. I suspect the majority of the time, node port will do the things. And as you get closer to production, you'll probably flip over to cluster IP and not use any of the other ones. We're going to use exclusively node port as we play today so that we can take advantage of that being a public port for outside the cluster. That means that we'll get to play with it from our local machine through the Docker router into Kubernetes. Any questions on service types?
So Rob, meanwhile here, there is a question under session Q&A from Anthony. Would there ever be a situation where you would want a deployment to be accessible by two services?
Ooh, good question. Would there ever be a situation where you would want a deployment to be accessible by two services? Yes. Stateful sets allow exactly that, where I have a headless service that manages the stateful set, and I might have a public service that would expose only a subset of those pods to the greater environment. In the majority of cases, though, one service is usually sufficient. And so I'll generally have a pair. I'll have a deployment and a service. And those two pieces will kind of be my core elements for each microservice. That is a great question. Thanks for bringing me to that one. I didn't realize that our session Q&A was live.
No problem.
Service types. Mapping services to pods. YAML config files. This is cool. So we built one here, and we built the YAML for that, but let's build a new one. I want to say new file. I want to build a pod.yaml. I'm going to say pod, and I've got some helpers that will let me do all the things, which is really sweet. .net. Okay, so we have some redundancy here. That's totally fine. In my image, I'm going to say hello.net. In this case, I have some resource limits. That's perfect. And my container port, that will be port 5000. That's what I specified. Cool. I just built up a pod definition using VS Code scaffolding that made that super easy. I would invite you to type these things out, though, because getting more muscle memory on how these things work could be really helpful. But as you want to spin up another one, grabbing these Visual Studio helpers works out really well. Resource limits. I want my memory to be limited to 128 megs of RAM and my CPU to be 500 M. So does that mean 500 CPUs? I'm not really thrilled with their units. This actually means a half a CPU. So I could have this be a half a CPU or an eighth of a CPU. Let's actually say a tenth of a CPU. Actually, that would be a tenth of a CPU. A hundredth of a CPU, or I could just say one CPU or 3 CPUs. Towards memory, I want to give this 2 gigabytes. So now it gets 2 gigs of memory and 3 CPUs. If you leave the resource limits off, then VS Code will say, hey, you need some resource limits. And so I can say, I'll just give this an empty object, and it'll say, okay, I'm good. So that's my trick for giving resources the details that it needs. Okay, so that's a pod definition. I have API version of v1, kind is pod, so my namespace is v1, my class name is pod. I have some containers that I've identified, the container port that I'm listening on, and I gave it some labels. In this case, I say name is .NET. I'm also going to say project is foo and company is bar, and all the other details that I want to specify. I might even say git hash is ABC123 and version is v1.2. I can specify whatever hardware labels I'd like here in this pod definition. I've got this pod definition, which does really cool things, but I want to build this as part of a deployment. So I'm going to say new file deployment.yaml. And then, yes, I would like you to build a deployment. .NET. Okay, so now I've got this, and it has this spec that specifies, or this template that specifies all the details associated with my pod. Let me just go grab my pod, not that. I'll just go grab my pod and I will set it in place here in this template. Because after all, that's exactly what a template is. I leave off the API version and kind, and I'm going to leave off the name. I'd like it to auto-generate it. But all the rest of the pieces are exactly from the pod. Now, in production, I probably won't ever use pods. I'll only use deployments. But in this exercise, we'll go build a pod, and then we'll build a deployment to get the feel for those. Similar things, I can spin up a service, specify all the details that I need for that service, and then start routing traffic into place. When I'm ready, I will say, and I haven't saved these, kubectl apply-f, and I will give it the path to my pod. And that will go spin up the content. kubectl apply is actually an upsert, a merge. So if it doesn't exist, it will get created. If it does exist, it will get updated, which is really, really sweet. So I'll say kubectl apply, and then I'll be able to say kubectl get all, and I'll be able to see all of the resources that I have running, including the service and the pod and all of the pieces. So our next step is here inside Kubernetes. We did number 5. And next up, we are going to do number 6. Number 6 will give us a good start for how we need to get started with Kubernetes. It'll give us a feel for kubectl. We'll build up a pod and a pod definition. And then outside, and of course, you can always check with my example here, and you can tell me what parts I got wrong. That hello Kubernetes will get us a feel for pods. Once we get comfortable with pods, next we'll build up a deployment and a service. Number 9 is really cool in that number 9 will say, here's the pieces that, here's how to delete the things. kubectl delete-f will pass it that YAML, and it will go delete all the things. So if you make a mistake and you don't like it and you want to kill it off first, you can delete it, or you can just kubectl apply over the top and it will get it in place. So let's trek into 6, 7, 8, and 9. We're also coming up on lunch. And so if you want to, go grab some lunch and come back, and we will begin again. It's about 10 minutes before 12. Let's kick off again about 12:30 and come check in. But I'll be here the whole time. And so let's go look into it. Before we go there, though, John has a question. Does cluster IP automatically repoint to node port? Is that container port 5000? Is container port 5000? Is that node port? Let me go back to that example because that was really cool. That's such a brilliant question. Right here. So the node port will be 32,000 something, and it will forward to the target port, in this case, 3,000. That target port is the container port, the port that the container is listening on inside the pod. So the node port is 32 something. The cluster IP port is 3,000 something. So those two will always be separate. But whether it comes in on the cluster IP or on the node port, it will forward then to the target port that will connect to the port on the pod. Yeah, that was quite the mind bender. Did that answer your question, John? Such a great question. Thank you. Oh, Ho-chan, we almost missed your question. Let's dig in here. kubectl get all. I can say kubectl get all, or I can say kubectl get pods. Now in this case, I don't have any pods, but let's say kubectl get service. And here's my service. kubectl describe service. Here's all of the things, and I have these labels. So I could say kubectl get service where labels. Let me double check what that command is. I think it's find, but that's columns, find name. Field selector, that's not it. No headers. I will go find it. kubectl get svc label equals app. Nope, that's not it. I will go find the command line that gets us the label. And when we come back at 12:30, then let's dive straight into those three exercises, and I will have that answer for you.
So it's a lunch break, Rob.
Yes.
We'll resume at 12:30 PST.
Yes. And if you come back early, jump straight into 6, 7, 8, and 9.
Okay. So I'm pausing the video.
Sounds great. I'm
Thank
not
you.
sure if lunch break was built in. Was that the appropriate choice?
Yeah. Because we started from 9:30. Yeah, it's good. 9:30. It's almost 2.5 hours. So that's fine.
Yeah, that sounds great.
Yep. Okay, participants. So we'll resume at 12:30 PST. Rob, I'm pausing the recording.
Sounds great.
Thank you.
I'm going to go grab some lunch too.
Sure.
I'll be right back, and I'll grab your question. So if you have a question, feel free to type it, and in a minute, I will answer.
I have one question. Can I?
Yes.
So what is the difference between ECS and EKS? EKS for equivalent to Kubernetes, and ECS, what is that? It is equivalent to Docker?
ECS is their homegrown orchestrator, and EKS is a hosted Kubernetes. So with ECS, it's kind of like Docker, it's kind of like Mesos. It's an orchestrator, so it runs containers, but you don't use kubectl to access it. It just kind of does its own thing behind the scenes.
Okay. And one query, some of the questions, as for example, there was a question that you answered regarding the kubectl. I did not find that question neither in session Q&A and chat. So where those questions are coming?
I saw that in chat.
In chat?
Did I see it in chat?
Chat.
How do I search a pod from different cluster according to metadata tag of the pod or FQDN or IP address?
I don't see the last question. I can see that where can I get the slides? And before that, does cluster IP automatically repoint to node port? Is that container port 5000 is node port?
It's the one right before that.
From Kevin? No, from whom?
From Hachan?
Okay. I can't see that question. I can see only the thanks.
Weird.
Rob. Yeah, from Hachan, I see only thanks, Rob. Where is that question? Anyway, yeah, I don't see that question under chat. Okay. Anyway, we'll resume at 12:30. Thanks, Rob.
Yep. Great question, Anthony. I suspect we'll start a bigger site, number 10, at 1 o'clock or 1:15. But if you only have until 1, then feel free to keep running through them. And if you want to reach out to me on Twitter at Rob_Rich, then we can dig into any questions that you have. Thanks for joining us for as long as you could. Wow, I just had a great chat with myself on mute. That was cool. Welcome back, everyone. If you're just joining us, we're going to dig into 6, 7, 8, and 9. But if you have any questions that you were thinking through over lunch, stepping away from the keyboard can be a great way to start to cement your knowledge. What things surprised you? What things didn't make any sense of things that we discussed this morning? If there are no questions, we'll dig straight into 6, 7, 8, and 9, and probably about 1:15 in about a half an hour. We'll dig into number 10, or if you want to get started on number 10 early, we definitely can. But about 1:15, we'll definitely switch over and dig into a bigger site. In Hello Kubernetes, we are wrapping our Docker image in a pod and scheduling that pod to run. Is this essentially saying Docker run hello node 0.1? Yes, exactly. That is perfect. That's exactly what we're doing. We are giving it a pod definition so that Kubernetes can schedule that container. Apache Arrow is actually based in containers if you want it to be. And so those jobs could be these little stateful or stateless containers that read from one source, write to the other source, and then go away. So Apache Arrow based on containers is one great resource. Another great resource, we looked at volumes really briefly this morning, and volumes allow us to store data much more durably. So we could think of that as a file store. So now I want to get images into place. So, maybe I'll dump them into one folder and then I'll have an Arrow job that resizes them and dumps them into a different folder. Or perhaps I want to get a database. And so I'll have a database and its data folder is stored in a volume. As we get farther up that chain, we'll probably have maybe an ELK stack or maybe a MemSQL database that has multiple clusters, multiple machines, multiple things in its cluster. And I realize we're conflating the term Kubernetes cluster and database cluster, but we'll have multiple machines, multiple containers that need to keep track of stateful resources. And so that's where we'll reach for stateful sets that allow us to maintain that quorum of containers inside of Kubernetes. So how do we get to that part where we get the stateful content? That's when we'll reach outside of pods, deployments, and services and look to other resources. What makes it really helpful, really beneficial for data architects doing this is that these processes spin up really, really quickly. And because they spin up so quickly, then we don't need to wait for a machine to boot, or we don't need to have extra machines kicking around waiting for that data need to move, or waiting for a request to come in for that data. There's times when we can say, let's wait for the request, and when the request comes, go spin up that container real fast and answer the request, which means much less demand on our resources. So we can use our data center much more effectively, much more efficiently by using stateful containers inside of Kubernetes.
Okay. Okay.
A great, insightful question. Thank you.
Yeah, I forgot to turn on the recording. So just when you started answering my question, then I started the recording just for our purpose. The question was how Kubernetes will help the day-to-day data engineering ingestion, like stateful, what Rob has explained. Yeah, just recording purpose. Yeah. Thank you, Rob.
Yeah, definitely. Great question. Pod spinning up, the deployment spinning up, and the services. I'm eager to get to number 10 because it is so cool.
Thanks, Ruben, for your comment in the chat window. So Rob, he had said that you can deploy databases and NoSQL with persistent storage. Also, if you use NiFi as ETL, you can deploy it on pods.
Yes, great comment, Ruben. Thanks. You unstuck? Or what are the things that you're currently stuck on? How can we help?
Hey, Rob, it's John.
Hi, John.
Hi, I'm doing the best I can, but I'm just going to take it in, apply it as much as I can later.
That completely makes sense.
My laptop went kaboom last night, and I'm just trying to catch up using Ubuntu for my desktop because that was the only way to save it. So do you have Ubuntu instructions for installation? You've got the details for Windows and Mac.
Yes.
I was able to get some of it done a little bit ago, but I don't think I can catch up with everybody. I'm just going to take in what I can.
Not to worry. If you come in here to 0 install, then here's
Right.
the instructions for Linux. So here's the Ubuntu instructions. That will get you the Docker CLI. The cool part about being on Ubuntu is you don't need that VM in the way. Once you've got
Okay.
Docker installed, then you also need to get kubectl in your path, and this will get you there. From there,
Okay.
You've got all the pieces. Or if you want to, you can, because you're on Ubuntu, then you might find that K3S might be a faster way to get you to a Kubernetes cluster. K3S kind of eliminates all of the non-default pieces. And so you'll get just a bare bones cluster spun up real fast. There's K3SUP, pronounced ketchup, K3S
Okay.
up, that can get K3S installed really quickly. So that might be an option to explore as well.
Thanks. I'm going to take some looking around. Enjoy the class, though. It's awesome.
I'm so glad.
No, I'm really happy to be here, even if I can't do
Yeah.
everything.
So we're going to kick off a bigger site. If you got tired of waiting for me to start, then by all means, get ahead, and this is awesome. If you're still catching up, then that totally makes sense, and you can do that as well. So here's what we're going to do for a bigger site. We have our front-end containers inside pods. We have our back-end containers. We'll put them inside pods. We'll create a back-end service in front of the back-end containers and a front-end service in front of the front-end containers. And then we'll tie them together. So I've put in kind of a cheat sheet of how the ports work. A user will go to localhost 32,000 something or other because it is the node port of this front-end service. That will come into the front-end service. The front-end service has a target port of 3000, so it'll go find those containers and come into the container on port 3000. The container is going to reach out to http://backend:5000. It's going to hit this backend service, and this backend name just happens to match the name of the backend service, which means that it's going to go straight into that backend service. The backend service will load balance across all of the pods here, and so it will go into, there's a typo right there, into port 5000. So if you're ready, kick off into a bigger site, number 10, and that will be really cool. If you got this site up live, I fixed that typo, so it now correctly says container port 5000 down here. So git pull, and you ought to have the latest. Were you able to get all of the pods and deployments and services spun up? Next up, rolling update is really, really cool. Let's imagine that we have a code change and somebody wants to make that code change. So here in 11, let's dig into that piece. And then we'll skip over 12 for now, but dig straight into 13. And then we'll come back to 12 in a little bit.
Hi, Rob.
Yes.
Yeah, Minmoy here. I mentioned that we have exactly 1 hour left.
Very nice. 1 hour left. It might be good to take a break from typing for a bit and let me show you some stuff about storing secrets. Is that a good move? I hate to interrupt you if you're in the flow. What do you think? Docker secrets. This is fun. Storing secrets. This one's another presentation that you can get straight from linking to from the slides or from the GitHub repo, and it will launch this site, which talks about storing secrets in containers. That'll be fun when we get there. Okay, secrets in containers. We have a few options of storing our secrets, and it depends a lot on, well, who we trust. Do we trust developers? Do we trust operations? Do we trust neither? I would say if you don't trust your employees, you're probably in the wrong business. But anyway, let's dig in. Secrets in containers. Where do we store our secrets? Well, it depends. Who do you trust? Our first stop is config files. We may choose to put it in a package JSON, or maybe we'll put it in a web.config, or maybe we'll put it in a manifest file. The cool thing about putting these secrets in this config file is that then we just Docker build and all of those pieces get baked into the container. That's really cool. From then on, we really don't need to worry about it. The container is closed and all of those pieces are baked in. So this is great when we trust our developers, but it's really easy to accidentally leak these secrets into source control. And so if I have a web.production.config or an app settings.production.config, then do I really want that in my source control? One of the benefits is that we don't need to trust ops with the secrets. They're just baked inside the container. Well, kind of, and thus I put the asterisks here. If I exec into the container and go ask it for its secrets, I have all the secrets. So it's not like we're really completely hiding them. Next up, environment variables. We talked about how we could pass in environment variables with the Docker run command. We can also pass in environment variables here in our deployment. So here's our container, our name, resources, ports, and we can say environment, let's do it in a pod. And there we go. And then we can say this one is, I would like to set the logging to true. I think it's a colon and it needs to be, nope, it's equals, my bad. There we go. Logging is true. I would like to say server URL equals http://example.com. You know, we can set as many environment variables here in our pod definition. And so if we're building that pod definition in a deployment, then of course we'll just specify those there. YAML indenting being a thing. There we go. So now we have our environment variables in our YAML. Now, the cool part about building our environment variables here is that they don't end up in source control because they're injected at the point where we launch it. So we might have a different deployment.yaml as we get into production. Now, there's ways where we can create layers of indirection where we actually put our configuration in config maps or in secrets and then reference those secrets from our deployments. On the upside, by passing these environment variables in as we launch the container, we don't need to worry about getting these secrets into source control. We don't need to worry about exposing these secrets to our developers. That can be really powerful because now we need only trust operations for these. Operations can quickly rotate the secrets without rebuilding the images. This is wonderful. On the downside, we do have to trust ops with secrets. And well, same with anything else, these secrets are now available in the container. So if my container gets exposed, my secrets also get exposed. That's just kind of the nature of how this game is played. So here's a third choice, secrets in the data store. I could put my secrets maybe in an Azure Key Vault or in a HashiCorp Vault. And now whenever I need to get at that secret, I can get my application to reach out to the store to go get the data. On the upside, I don't need to keep these, I can hide these secrets from both dev and ops. Only the application can read these secrets. And if the application needs to get the secret every time it uses it, I can rotate secrets really, really quickly. On the downside, this is probably the most complex of the solutions because I need to, well, I need to get my application go reach out for the secrets every time. So I'm implementing this in each application. So which is best? I love this. This is a, I'll pull up this video a little bit clearer here. This is a, let me make that a little bit bigger. This is a clip from Police Academy, and I will actually mute it so that we don't have to compete with that. And it talks really nicely about secrets. Here's the man closing up his shop, and he wants to lock his vault. So he puts the one padlock. Here's the bear trap. Set the bear trap down. Okay, now pull the grate. We can imagine the various layers of indirection where we're obfuscating our secrets in interesting ways. Here's the security alarm. Here's the backup security alarm, or maybe this is the red herring, the honeypot. We've got another honeypot. Here's the door. Lock the door. Are our secrets safe yet? Have we protected all the things? A grate goes across. Another grate. The barbed wire fence. Electrify the fence. I think our secrets are definitely safe now. We've done enough layers of indirection to make them really safe. He walks around the corner. He goes to the ATM, puts in his card. He's going to type a few numbers. Hello. Hello. And like any 80s movie, that's where he gets taken. Here's an 80s movie cliche. The guy with the big silly... He goes, ah! It's really fun. So as we look at this analogy, where were our secrets the most safe? When we look at these different choices, the secrets in the data store seems the most safe, but where do we store the secret to authenticate into the vault? Well, we have three options. We can put it in a config file, we can inject it in as environment variables, or we can put it in the config vault. Well, where do we put the, so we want to use config vault, that's the most secret. So where do we put the secrets? Well, we put, and you can see this playing out as we close more and more doors. The lock, the key to the lock needs to be outside the door. And so we end up with these three options. Where would you like to choose to put your data most safely? Well, it really depends on what you trust and where you want to put those details. If you put it in a config file, you need to trust your developers and you need to trust source control. If you choose to inject it in as environment variables, you need to trust operations. And if you have a secret store, then you need to figure out how to authenticate to the secret store, probably using one of the other two. And you need to bake that detail into every application. Now there is role-based access control, RBAC, which kind of mirrors a secret store. Well, kind of. RBAC is really interesting in that RBAC takes the identity of the container as the piece. So it's kind of like an environment variable. It's what you are instead of what you have. But now how do I know that that container was launched correctly? RBAC is really interesting. So when storing secrets, there isn't really the magic bullet, but rather there's a mechanism for choosing the most appropriate way that fits your needs. What are the ways that you store secrets, and how have you found it effective to store secrets? Secrets are really cool. Okay, storing secrets. I'm glad we had a chance to kind of dive out of the code for a bit. Docker Hub is really fun. Docker Hub allows you to push content into Docker. Now, we built a few containers over the course of this day, and you can choose to push them up to Docker Hub by creating a free account in Docker Hub. Or if you'd rather experiment more in private, you could spin up a container registry that works exactly the same, either in AWS or in Azure or in the cloud of your choice. If you're on-prem, you might have Artifactory or Nexus as your cluster, as your container registry, and you can do that there as well. So let's spin up into the Docker Hub one, number 13. How did you like Docker Hub? It's fun being able to create your own images. The cool part is that these images that you create are no different than any of the other images that you were able to pull. Now that you've got them published, you can delete them off your machine and pull them again, or your coworkers or friends could pull these images and start either building on top of them or using them verbatim. That's really cool. As we start rounding out towards the end of this workshop, there's definitely a whole nother section about deploying all of this content onto a cloud. And I would invite you to continue on and look at deploying to the cloud. I've suggested Azure here, though you can definitely deploy to Amazon or to Google just as easily. I just had to pick one for the docs. What are the things that you wish we covered that we haven't yet, that we can talk about for the next little bit? If not, then we'll get to talk about my favorite things. We've probably made quite a mess today. We've created a bunch of containers. We've created a bunch of images. First step, let's go through all of the things that we created in Kubernetes and clean these out. kubectl get all. Now we may see a bunch of deployments, a bunch of services, a bunch of pods. We can say kubectl delete service / hello node, and that will delete that service. We can do the same thing for deleting all the deployments, or we can say kubectl delete -f pod.yaml, and that will delete all the content for that pod, or deployment.yaml. If we want to as well, we can pass in an entire folder like the K8s folder. And at that point, then it will delete all of the things in all of those YAML files. That can be a really, really good way to get started deleting the things. Once we've got kubectl get all, once we've got all the Kubernetes things deleted, we still have some Docker things. Remember, Kubernetes was just automating the Docker pieces. So Docker container list. Now we may have a bunch of containers. Here's a container that I have that's just kicking around. I'm probably done with it. So Docker container rm-f eb0c7. In this case, I'm not actually going to remove it. I'll just say stop so that we can continue poking at it. But we could go remove all of those containers that we need to. Docker container list. Now it looks like it's gone. It is, but it isn't. Docker container list -- all. We can see that here are all of the containers that are stopped. Now I could come through and I could say Docker container rm and -f 848 and loop through them. And that's interesting, but there's actually a shortcut. I can say Docker container prune, and it will go delete all of the containers that are stopped. I'm going to say yes. And now all three of those containers are gone. Docker container list -- all. And I can see that I don't have any containers running. Well, technically, I still do have the Kubernetes control plane containers running. Here, if I come into Docker desktop settings, and I choose Kubernetes, we have the option to show the system containers, but in this case, we didn't have that running. If we did say show system containers, it's going to restart Docker, which I won't do, so I'll just hit cancel. But at that point, then we would see all of those other containers that are making the Kubernetes process work. Okay, so we cleaned out all of our containers. Docker volume list. Here's all the volumes that we built today. And you may also have some volumes that you might have created before. So work with care here. this will delete the data that you have stored in them. If you only started today and you have some volumes, you can do a similar thing. Docker volume rm, and you can give it the first few characters to delete it. Or if you want to delete all of them that aren't in use right now, you can say Docker volume prune. If you want to automatically put the yes straight away, you can say Docker volume prune -f, and now away it goes. We deleted all of the Kubernetes resources, all of the containers, all the volumes, Docker image list. Now here's a big pile of mess. We did a lot of things. We did all of the front end containers, all the back end containers. You may not be ready to delete all of these images because you may not be done playing, but let's do that. Let's say I want to delete this one, Docker image rm hello.net. Great, I just deleted all of these layers. Docker image list. Now there's some of them that say none here and none here. So how do I delete that? Well, similar to a prune that we did with volumes and containers, I can say Docker image prune -f, and it will go through and delete all of the things that had nones on it. Docker image list. Now my list is much tidier. Oh, I've still got that one. Apparently I built that one again. Docker image rm. And so you can get this to be quite tidy by deleting all of the containers that you're done with here. If you want to run all of these prunes at once, you can say Docker system prune -f, and it will do containers and images. And if you pass it a -- volumes, it will also do volumes. So now I'm pruning all of the stopped containers, all of the detached volumes, and all of the images that don't have valid tags. Now, Docker image list. I didn't prune all of the ones that did have tags. So, the front end container and the back end container, those didn't get pruned. But all of the other ones, all of the none containers did get pruned. So once I've got all of the images pruned that I don't need, now I've really lightened up Docker. There is a UI for doing this a little bit here in dashboard. I can come into the Docker UI and kind of get a feel for the images, and I might want to run them or delete them. But I would argue the command line is much more powerful than this. This interface is okay, not great. But you may be looking for other interfaces in interesting things. Let's pull up a Kubernetes interface. Not there. Here. If I say kubectl UI, it will launch this dashboard. Now this dashboard is interesting. It gives us lots of interesting metrics. We can dig into all the pieces and look at all of the Kubernetes things. But this dashboard is dangerous. And it's dangerous because there's this create button right here. Now, why would that be dangerous? Well, I could then walk through this wizard and start to schedule my own pods. Now, maybe the pods that I wanted to schedule are what you expect, but maybe I'm a nefarious actor and I want to schedule a crypto mine on your machine. By default, this dashboard has no authentication and is not exposed publicly. But if I flip this over from a cluster IP service to a node port service, or if I put a quick ingress in front of it, then it is unauthenticated and public, which means that now anyone could schedule anything. In fact, Tesla lost control of their Kubernetes cluster. It became a crypto mine because they left this dashboard open. Please be careful with the Kubernetes dashboard so that you don't accidentally get your cluster taken over. Let's talk about some of my other favorite best practices here. Actually, I think we have a little bit. So let's talk about choosing a cloud. As you're ramping up into choosing a cloud, which one would you want to choose? Should you choose Azure, Amazon, Google? For the most part, at the scale that we're working on, they all pretty much work the same. If I'm using Azure Kubernetes or AWS Kubernetes or Google Kubernetes, they're all Kubernetes and they all work just fine. I may choose a service because I've already got my content on it, or I like or don't like a particular technology or vendor, or maybe it has a particular service that I really enjoy. Now, the cloud vendors are watching each other very carefully and trying to keep up with the Joneses. So if you find a service that is really interesting, wait 6 months and the other vendors will have that service too. But choose the service that makes the most sense for you. Again, walk into your IT shop, say AWS and Azure and GCP, and somebody will talk to you for an hour about which one is their favorite cloud vendor. And I agree, that's the proper cloud vendor for you. What's cool about all of the rest of these is as you're getting these spun up, you can do this with any of the cloud vendors. Once you get to here, you're running kubectl commands. You're just giving it a different registry name. kubectl will work exactly the same. You're just giving it a different context. The Kubernetes experience that you will have on the cloud is the same Kubernetes experience that you had locally. It is really cool. You'll be really excited at how quickly these last few things come together. So software architecture for the cloud. Let's dig into this presentation because this one is really fun. And then we'll talk about my favorite best practices. Software architecture for the cloud. So when we look at what does cloud mean, we're often given this diagram. And this diagram is interesting. It's, a cloud vendor, or it's a cloud diagram where we talk about in the olden days, we would build up everything. And then we wanted to outsource infrastructure. So, all of these pieces we outsource to our cloud vendor. And then we wanted to do platform as a service, and then maybe software as a service. Where does containers fit in this metaphor? Well, it's kind of right here. Actually, it's kind of right here. Virtualization, operating systems, we don't need to worry about the operating systems, but we kind of do because we have this shared mechanism. With platform as a service, we often have very little control over the file system layout. We only get a certain small folder, where with containers, it's more like infrastructure as a service. We can decorate it anywhere. But unlike infrastructure as a service, we don't need to patch it. We don't need to worry about the operating system. So it fits nicely right here in the middle. So what is the cloud? The cloud. The cloud is instant hardware provisioning. We don't have to wait for a purchase order and go rack servers. We've outsourced hardware management. We've built utility computing. We're paying only for our usage. That's kind of what makes it cloud. That's what makes it cloud more so than just a colo facility. So what is the cloud? Spin up and spin down things quickly. Pay only for what you use. What is the cloud? Small bundles of elastic scale functionality. We could think of this as cattle, not pets. If we have a pet, we may dress it up, we'll give it names, we'll take care of it and play with it. In time, that may get to be burdensome. We want to focus instead on cattle. Here's a bunch of sheep. And so now we don't really worry about each individual thing. We just kind of worry about the herd as a whole. We want to get to the point where we're not babysitting our pets. We're kind of forming our cattle of services. Put this in technology terms, we don't want that one fancy server. We want a big wall of identical servers. Or taking it a step further, we want our cloud to provision a bunch of things and we'll just set our containers in place. That's really cool. We need to make some assumptions here, though. When we outsource those pieces, we may not have the things that we expect. So, for example, the machine isn't durable. It may not be the same machine next time you wake up. Maybe after that former request, before the next request, is the time that Kubernetes decides to reschedule that pod or to spin up another pod to meet your scaling requirements. We need to learn not to care. We need to architect for this type of lack of durability. So that state that may be in this container needs to not be in the container. We need to not have really intense startup times of prepping all of the cache and doing all of those things. We also need to understand that the disk isn't durable. Maybe this is the moment that the cloud hardware node fails, or they decide to upgrade that node, and so they reschedule all your pods the other place. If I'm saving data in my app data folder, by the time I reach the next request, it may be gone. The process also isn't unique. We hit this problem even in our data center as soon as we have two machines hosting the same content. We can't assume there's only one process running. Maybe I did a request to server A and I saved my data to server B. Our application needs to be able to handle that by taking all of the state and storing it somewhere else. This one is fun. Clearing the cache is hard. Clearing the cache is really hard because we got to tell all the other guys to clear their cache too. We can't just clear the cache on this one process or this one machine. So now do I keep a list of all of the other containers and tell them to clear their cache? Well, what if I have 100 servers or 1,000 servers? I can't just, well, click clear on them. Should they then go tell everybody? It's probably better if we put our cache in a separate spot. Let's use Redis as a service or another platform as a service that gives us that cache out of process. So when we move to the cloud, we need to understand that the things under us aren't durable. Now, if we plan for that, that's perfect. We can create processes, ETL processes that are reentrant so that as we're moving this data, we can notice that the data already exists in the destination and not try to overwrite it or append to it. If it's reentrant, if we do a merge instead of an insert, then we can ensure that our data is consistent in all the places. Data store as a service. I love this one. When we look at data store as a service, we outsource all of the pieces of keeping our application up and alive. If ever you've gotten woken up at 2 in the morning because the database server went down, outsourcing that to somebody else is really, really nice because they need to worry about keeping the server alive and point-in-time recovery and keeping it up at nearly 100% of the time. You've outsourced that problem to them and they can handle it. It's really nice. If you're doing it yourself, you probably need to do some wacky things with backup and geo-redundancy, and your cloud provider is going to do all that for you, which is wonderful. Stateless services. Build small services that can operate independently. Whether it's 2 requests on the same box or requests spread across 1,000 boxes, your application should be able to scale horizontally in exactly that way. That's why we've grabbed utility computing. We want, pardon me, we want commodity hardware that is able to scale in the way that our application needs, just by building it out that way. Now, that does mean that we need to ensure that our state isn't stored inside our services, but is pushed out to a more durable storage so that our services can be stateless, reentrant, and more durable. So microservice architecture, provisioning is easy, but with these smaller pieces comes the complexity of stringing these pieces together. We got to see a little bit of this in the way that we strung together our microservices in Kubernetes. We built lots of small microservices. The benefit here is that we got to upgrade our front end without taking down our back end. That was really, really cool. And then we can redeploy each piece as it comes into place. That's cool. Microservice architecture. The unit of deployment is a module, a feature, a tool. It's no longer an entire system. But that does mean that we have complexity around stringing these pieces together. How do we do a unit test of our microservice architecture? Well, we probably need to push a thing all the way through. It's no longer a unit test. It's now an end-to-end test through all of the services. We will stitch these services together into kind of a mesh of services. This mesh we can think of as all of the pieces, all of the little pieces of software, of application that makes our project work. Lots of little microservices connected together in all of the pieces. We need containers. And that's where we went today. So we took a look at containers and how we could string them together. In Docker, we built that configuration as code that gave us really, really reliable infrastructure. And then with Kubernetes, we saw how easy it was to replace things without downtime. That was cool. On the upside, microservices are easy to deploy and easy to change, easy to scale. On the downside, the system is much more complex now outside these pieces, where it used to be complex inside the pieces. We haven't eliminated the complexity, we've just moved it. So one of the challenges, how do I discover the URLs of all the dependent services? We saw that as we created our front end connecting to our back end. Now I need a service discovery data store or a load balancer in front of each piece. We saw how Kubernetes solved that really nicely. Communication between services, HTTPS, message bus, service bus, database, event store. There's mechanisms now where we can communicate asynchronously between these services. That's really cool. So how do we know when we've gotten to microservices? How do we know when we're done? Well, if we're sending messages between two machines, we also need to consider that these processes aren't durable. I want to get the message there exactly once, but what happens if a failure happens in transit? What if two boxes handle the message simultaneously? What if no boxes handle this? We can build systems that are at most once or at least once to get our data there securely. Microservice architecture. Design deterministic functions. Now, the ideal is if you play it again, you'll get the exact same answer. We're kind of reaching towards functional programming here, perhaps. But as an ideal, this doesn't always work. The side effects are the things that make our applications do great work, like sending an email. I can't just exactly send the email again and see if it works. If I send the email twice, that could be bad. It may be more desirable to send the email 0 times rather than 2 times. Creating a record, inserting a new record. If I insert the new record twice, is that better? Or if I insert it 0 times, is that better? Or should I check to see if it exists and then insert it only if it doesn't? These are some of the things that we look at when we look at microservice architectures. We can think of this as eventual consistency. When we look at eventual consistency, we might think of scenarios like airline ticketing or shipping tracking numbers or bank statements. If I go into a Starbucks and I go buy something, and then I go check my account, my bank account, it probably isn't there yet. But by the time my statement arrives at the end of the month, it definitely is there. Eventually, my bank account is consistent. I'm going to actually pivot off of software architecture, and let's talk about some of the Kubernetes best practices. This is really cool. Kubernetes best practices. This is kind of the cheat sheet of the best of all the things. And after this, I'd love to learn about your best practices. So containers are the unit of scale. With containers as that unit of scale, If I want more than one, I have more than one container. So as we noticed, if I have my database and 3 Redis servers and 10 web servers, if all of those processes are baked into one container, I don't have the ability to scale those independently. Instead, I will put each small piece into its own container. As I reach towards microservices, I'll end up with a front end and a back end. And now I can scale each of those independently. Maybe I don't need to scale up my auth service, but I do need to scale up my shopping cart service. Microservices and containers allow us to do that. Here's a good rule of thumb. We hit this a couple of times. 1 process per container. Docker is going to monitor that process. And if that process ever becomes unhealthy, it can stop and restart that container or destroy that container and create a new one. If I have more than one process running in my container, Docker can't do that because it doesn't know if one of them stopped. Should it kill the container? The thing that is replying, probably the host process, may still be alive while all the child processes may or may not be functioning. 1 process per container. Simultaneously, 1 container per pod. In Kubernetes, the pod is that unit of scale. And so if I put multiple containers inside 1 pod, I'm back to that distributed monolith problem. Use a managed data store, a database as a service to be able to get most durable data outside of Kubernetes in a place where you've outsourced that liability. That's perfect. If you do need data stores inside of Kubernetes, then look towards volumes and stateful sets to be able to get at durable storage outside of in containers that is actually stored outside of Kubernetes in a more durable place. Rebuild and deploy production images frequently. One of the things that I often get asked, and I didn't actually get asked this today, is how do I do Windows updates in containers? Well, Windows updates in containers isn't really a thing. Rather, we have this configuration as code, this script that explains how to rebuild the container. So every Patch Tuesday, go kick off all of your container builds and deploy them into production. I say maybe once a week, get all your ops people to go push all the buttons on all the builds and redeploy them. That can be a really powerful way in keeping all of your systems patched. Or leverage a tool that will identify vulnerabilities in your containers and rebuild those containers to get modern dependencies into place. You don't patch the containers once they're launched. You patch the container dependencies as you build them. Store secrets carefully. We talked about this one quite a bit where we talked about the 3 places you can put them. You can put them in config files, you can put them in environment variables injected in, or you can put them in an external store. Understand the things that you trust, the places where those secrets may get exposed, and choose carefully. At the end of the day, though, I can Docker exec into that container, and I can grab all of the things that that container knows. So at the very end, there isn't really a place to store them that is not exposable, that is also useful. Choose carefully where you store your secrets. Kubernetes secrets. As if I store a Kubernetes secret, it is stored as base64 encoded on every node. Now it needs to be on every machine in the Kubernetes cluster because if I start a pod there and it needs the secret, it needs to be able to spin it up. Inside Kubernetes, there's a mechanism since 1.13 to store these encrypted by default. I wish that setting was on. It is off by default. So please turn that on to encrypt your secrets stored in Kubernetes, or choose to store your secrets in a key vault like HashiCorp Key Vault or Azure Key Vault. Production config as environment variables. If you're able to expose your configuration, please expose as much as you possibly can so that others can consume this data in interesting ways. Operations will love you if they can tune the containers with the resources or resource limits or configuration and logging details. They'll be able to tell you exactly what went wrong in the container. That's really cool. We talked about the Kubernetes dashboard. It's really easy to accidentally make this public and to therefore lose control of your container. If you can, use kubectl and the Docker CLI instead of the Kubernetes UI. I would invite you to version control your YAML files. I like to do a monorepo type of experience where my Kubernetes YAML files and my source code and my Docker file live all together in one repository. At this point, I now have the exact instructions to build this version of the code in this version of the code. And so developers and operations can fire this up. The CI server can fire this up and get at exactly the version that I need to be able to deploy. Leverage caching layers. We talked about how moving the package JSON line up allows us to leverage the cache of our libraries. Now, we might consider this to be in direct opposition of the Patch Tuesday update rebuild. And so on your build server, you may choose not to use the cache. You may destroy the cache on the way in or pass in --no-cache into Docker to avoid using those caching layers. Docker ignore is a great way to reduce the impact of the Docker file. We use that to avoid copying in built assets, unversioned assets into our containers. Ingress over load balancer. Load balancers will spin up with each service of type load balancer, where ingress will be able to map DNS names across many services. So you may have less ingress than services, and that can be a really elegant way to avoid that resource contention. On the downside, the default ingress only supports port 80 and port 443. Which means if you want an unusual port, you're back to doing a service of type load balancer. Deploy the services before you deploy the deployment. We looked at that as we were spinning up a bigger site where we needed to start the backend. We needed to start the backend service before we started the front end container so that we knew that that container had the environment variable, the DNS entries to be able to reach the backend service. There's quite a few other best practices in here, but I want to give you time for the things that you find as best practices. What are the things that you've enjoyed as you've used containers? What tools and practices do you find most effective? Also, how did we do in this workshop? What are the things that you wish we had covered more deeply? Or what are the things that we didn't explain very well that we can do better? What are things that we did great in this workshop that you'd like to see done again if this workshop was repeated?
No, Rob, I believe it is wonderful workshop. You have covered everything. Means starting from the hands-on, you were very much interactive, and last the best practices that you have explained. It's phenomenal.
I'm so glad. I'm really glad that I get to share this with you today. It's so much fun getting to teach this workshop. It's unfortunate we're not in person because I love to get to wander around the room and interact with you some more, but I'm really glad that you were able to attend today. Next up, I believe there's a session evaluation, and I would love your feedback of how we can make this workshop better and what you really enjoyed about this. What's our next session that kicks off at 2:30?
No, it's a keynote session will start from 3 o'clock.
Ah, very nice. So we have a half-hour break.
Yeah. So thank you so much, Rob, for your wonderful and interactive presentation. And I appreciate that all the attendees for their questions and interactions during the session. I'd request attendees to contact Rob if you have any further questions. Please provide your valuable comments and feedback to us. Thanks once again for joining today's tutorial. And I hope that you have gained insights about Kubernetes from this session. Have a wonderful rest of the day, and thank you for being a part of this year's DataCon LA. Thank you.
Thanks, everyone.
Thank you.